Alright guys, we're going to go ahead and finish up 9a. So we're talking about functions and the different ways that functions can be expressed. Remember that a function is it's just a relationship between x's, or values for x, or your independent variable, and then those corresponding values for y, or your dependent variable. Okay. The last thing we looked at was actually plotting ordered pairs. Okay. And we had basically got down here where it says consider the example about the growth of bacteria. Okay. And so we've got a table. So we're going to use a table to show this relationship between, we've got two variables here. Our independent variable is going to be time. This is sort of like our values for x. And then our dependent variable is going to be the actual number of bacteria. Because if you remember from that problem, guys, we start out with one bacterium, and then over that next minute, that bacterium doubles, so now we have two. And then over that next minute, the two double into 4, etc. Okay? So the time is really determining the number of bacteria. Or in other words, the number of bacteria is dependent upon how many minutes have passed. Okay. All right, well, let's try this. So we're going to start out, we're going to let time be 0. Okay. Let's see, the cursor isn't showing up over here too well. Okay, there we go. Okay, so when time is 0, we have 1 bacteria. Okay, and then over that next minute, so when the time goes from 0 to 1 minute, the end of that 1 minute, then we're going to have, if you double 1, you get 2. So we're going to have 2 bacteria. Okay, and then when time is 2, or over that second minute, we're going to, the number 2 is going to double, so we're going to have 4. And then over that third minute, the 4 is going to double, and we're going to have 8. And this process just continues, okay? And the 8 doubles, and you get 16. Or if you remember, you can treat the number, because the bacteria is doubling for every minute, you can actually use an equation. You can say y, which is the number of bacteria, is equal to 2 to the power of x, okay, where x represents time in minutes. And this is a type of function. Usually in an algebra class it's written like this: y is equal to 2 to the x power. And so what's happening here is, as you plug different values in for x, or these different values of time, then you're going to get different outputs, okay? Different values for your independent, or for your dependent variable. In other words, it's going to give you the predicted number of bacteria, okay? So for example, you know, when x here is 1, 2 to the first power is 2. When x is 2, or after 2 minutes, 2 to the second power is 4. After 3 minutes, 2 to the third power is 2 times 2 times 2, which is actually 8. Okay? So this is the actual explicit function right here. But we can see this behavior in this table. And I'll actually go ahead and let's do a little graph. Okay? And so what we would have on the horizontal axis would be time. Okay? Our independent variable is always on the horizontal axis, and this is time in minutes. Okay, so I could calibrate this. Start here at 0, then 1, then 2, 3, 4. Okay, and you can just keep going. And then the y-axis, or the vertical axis, represents the number of bacteria. Okay, so I could calibrate it. 1, 2, 3, 4, 16, and all the way to 16. Okay, so if I started plotting these ordered pairs, my first ordered pair, whenever x is 0, or when time is 0, then we have 1 bacterium. Okay, for some reason I cannot see the cursor over here. Anyway, we would plot this ordered pair, 0, 1. Okay, so here's 0, and you go up 1, so it'll be right there. And then the next ordered pair would be 1, 2. Okay, so you go to the right 1 and then up 2. The next ordered pair is 2, 4, so to the right 2, up 4. And let's see, it's about right here. And then 3, 8, so to the right 3 and then up 8. Let me see where 8's going to be. 4. Okay. Now this isn't perfect, of course, but relatively close. And then 4, 16, so to the right 4 and then up 16. That puts us about right here, guys. And when you connect these ordered pairs or connect these dots, the shape of this is called an exponential curve. Okay, and if you recall, that example that we did in 8A was concerning the exponential growth of bacteria. The bacteria was growing exponentially because it was doubling, which means the growth rate was 100% each minute. Okay, and so what this curve does is it shows you that as the minutes pass, the number of bacteria increase. And it's not a fixed increase either. This is actually a curve that gets steeper and steeper as the minutes increase. Okay. Anyway, that's another example for you. Now what we're going to do is talk about domain and range. And these may be terms that you've heard before. So every function is going to have both of these. The domain of a function is basically the set of values for the independent variable. Okay? And then the range is going to be the set of values for the dependent variable. So if I go back to this previous example, since time was my independent variable, these values right here represent values of the domain. Okay. And then my dependent variable was the number of bacteria, and these values, the 1, 2, 4, 8, 16, these represent values in my range, or in the range of this function. Okay. All right. So let's get a little bit more practice with this. Let's look at a different type of function. So what this function does, if you look, it's the graph of a function that we're seeing. It shows us how age is related to weight, or how weight, a person's weight is related to their age. Okay? And so looking at this graphic, because age is on the horizontal axis, age is the independent variable. Furthermore, guys, age represents values of the domain. Okay? Because as you're growing up, on average, your age will determine your weight. Or in other words, your weight is a function of age, or it depends on your age. Okay? And so weight would be your dependent variable, and consequently these different values will comprise the range. Okay? So let's talk about these ranges of values. So for the domain, if you're looking at this function, we start off at 0, so that's the time at which you're born. Okay? And this would, on the vertical axis here, this would represent your birth weight. And then what happens? Well, this starts to go up. Okay, bye, Tim. This starts to go up. It gets even steeper right here, because this is typically when, kids or preteens hit their growth spurt. And then it starts to kind of taper out as the years progress. Okay, so, on average, people tend to gain weight as they get older. There are exceptions, of course, in which people, they reach adulthood and then they more or less stay the same. As they get older, they even lose weight. But anyway, if we have to quantify the domain would be all these values, all these different ages. So this goes to about, a little after 40, 41 or 42. So we could express the domain as all the values from 0 years of age all the way to, we'll just say 40 years of age. Okay, so it includes all the values in here. And then the range would be the range of those weights. Okay, so when you're born at 0 years, let's say this is about, it's hard to tell what this is, but let's say this is 10 pounds. Okay, so this is a big baby. So you start out at 10 pounds, and then as you grow all the way up here to, let's say, 40 years, you end up weighing about, we'll call that 125 pounds. Okay, this maybe is a rather small person here. But this whole range in the weights, because the variable weight is the dependent variable, all these values right here represent values in the range. Okay. All right. We're going to look at one last example. So if you're creating or using graphs of functions, first of all, you need to be able to identify which variable is your independent versus your dependent variable. Okay, so like we did in this last one. Identify the domain and the range of the function. Make a graph using the given data. So when I say make a graph, I mean do something like this. Okay? This is the data right here. And then you plot that data on a Cartesian coordinate system. Okay? And it says, if appropriate, fill in the gaps between the data points with like a smooth curve. And then you can use that curve or the graph of that function to make predictions. Okay, so for example, in the context of this problem, if let's say out here is 50 years, if this curve were to follow its natural trajectory, well, maybe it is still increasing, but it's not increasing very much. Let's say that, if it continues this current path, then this would be the data point that represents the weight when this individual hits 50, which would be maybe a little bit more than 125, but not a whole lot more. Okay, so these functions, or the utility associated with these functions, is once you are able to establish this relationship and kind of quantify the relationship, then you can start using the function to make predictions, okay, for data values in the future. Or like up here, we're concerned about bacteria. If we want, since we know this is the relationship right here, we want to see how many bacteria there are after 10 minutes. We just plug a 10 in for x and see what 2 to the 10th power is, and that'll tell us the number of bacteria. Okay, so that's the real power there in functions. We use them to model behavior. So we're going to look at one last example of a function. So let's read this here real quick. So you guys are intuitively familiar with this information. The number of hours of daylight varies with the seasons. Okay, so unless you live on the equator, there's going to be a variance if you live in the northern hemisphere or southern hemisphere. Now, the farther away from the equator you are in latitude, the more variation in daylight you're going to experience through the seasons. So use the following data for 40 degrees north latitude. So, 40 degrees north latitude, Little Rock is around 34 degrees latitude, I believe, so it'd be a little bit north of that. So I would say maybe Chicago, perhaps. To model the change in the number of daylight hours with time. So the number of hours of daylight is greatest on the summer solstice, which is around June 21st, when there are about 14 hours of daylight. Okay? And this is these numbers are real similar to what it's like here in Little Rock as well. And then the number of hours of daylight starts to decrease after the summer solstice and reaches its smallest value on the winter solstice, which is around December the 21st, where there are only 10 hours of daylight, roughly. Okay? And then on the spring and fall equinoxes, which fall on March 21st and September 21st, there are 12 hours of daylight. They call those the equinoxes, guys. That prefix equi means equal. So that means on these two dates, there are just as many hours of daylight as there are hours of nightfall, okay, or darkness, in other words. And this cycle repeats, okay, so there's an ebb and flow, an ebb and flow every single year. And so what you could do is you could think about this in terms of a function. You could say, okay, t, or time, the time of the year, that's my independent variable, and then the number of hours of daylight, h, that depends on the time of the year. So h would be my dependent variable. And so you could write it as a function like this. H is equal to, or the value of h depends on the time of the year. Okay, so the domain is all times of interest, say over a 3-year period of time. And then the range would just be 10 to 14. Because if what we're measuring is daylight, that variation in daylight is just going to go from a minimum of 10 all the way to a maximum of 14, and then that process is just going to repeat over and over and over. Okay? And when that process repeats, we get a function that looks like this, like a wave function. Okay? And if you were to ever take a course in trigonometry, you would study functions of this nature. Let's talk about this one just for a second. So as you can see, as time progresses, okay, remember it takes 365 days to make a year. So we start out at the winter solstice, where there's only 10 hours of daylight. And then we go through spring, okay, the number of hours of daylight is increasing. Then we reach the summer solstice, where there's a maximum of 14. And then it starts to decrease again through fall, and we're back here at the winter solstice, okay, where there's only 10 hours of daylight. And then over that next year, that process just repeats. Okay? It just keeps doing that year after year after year. And so, anyway, this would be a different type of function. Okay? A function in which the values for the dependent variable, they are alternating, or they are cycling, okay, as we go through the years. All right, so I think that's about it, guys. So this is just kind of a little introduction to functions, or this relationship between values of an independent variable and those corresponding values of a dependent variable. All right, and then we're going to finish up this course with 9b. Okay, in 9b we're going to study the behavior of specifically linear functions. Okay, so in other words, a relationship between two variables that's linear. And we've already seen this. We saw this in 8a, okay, where values in that dependent variable increase by a fixed amount for each increase in value of that independent variable. Okay. All right, well, I think I'm going to stop this one for now.